Hello, this is Darren Pulsipher, Chief Solution Architect of Public Sector at Intel, and welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. On today's episode, Resilient Data with Disruptive Comms with special guest host, Dr. Anna Scott.
Welcome, everybody. I am Anna Scott. I have the extraordinary pleasure today of actually hosting the podcast of Embracing Digital Technology, and I actually get to interview Darren this time. So welcome, Darren. We are delighted to actually be in a position to talk to you and put you in the hot seat as opposed to in the host seat. So welcome.
I'm looking forward to it. I really am, and I hope that Anna does more hosting. Give me a break. I could take a vacation maybe sometimes.
I would love to do that. So we will figure out how to make that happen. So,
all right. So what's on your mind today, Anna?
You have developed a really interesting technology that has really broad utility. And really the focus of that is how you can do secure and efficient essentially data management that allows and enables artificial intelligence as well as complex data analytics, and do that at the edge, and do that when you have things like limited bandwidth or you have interrupted service for a long time, so that instead of just saying, hey, I've got this incredible network connection that allows me to go to the cloud and be continuously connected to the cloud, you really are informing this architecture saying, hey, maybe the cloud's there, maybe it's not. Maybe you get it for 5 minutes and then you lose it for an hour. And maybe when you are connected, you don't have this beautiful, fiber connection. Instead, you're on a really low bandwidth connection. But you still need to be able to communicate. You still need to be able to do the AI. So I was really hoping that you could talk us through, right? How did you solve that problem? Like how that is a tough one. What was your basis of saying, what do you do about that?
Well, yeah. I think it's really interesting. When we first were approached with helping to solve this problem, my first thought went back to work I'd already done with Toyota on their connected car cloud, which was very different, but there were some things that were similar. So I started there. I said, all right, I know how to do distributed data management. I've done that before. Mm-hmm. I think I can figure this out. But then the customer we were talking to said, oh, and by the way, there's this weird thing called DDIL. And I went, what is DDIL? Disruptive, intermittent, low bandwidth, low latency. All these really, I don't have really good connectivity. And it was interesting because the way that the customer unveiled that to us was not all at once. It was over time as we kept asking more and more questions, which was great. Because if they would have just given it to us all at once, I would have just folded up and curled up in a ball in the middle of the room and just said, forget it.
I don't believe that, but that is a super hard problem. Yeah.
It is, but the way that they led us down the path, or that we discovered the path with them, helped us identify certain design patterns that were out there that are common design patterns that we could use and utilize. And it really opened up the architecture through this discovery process that we had with them, which was really kind of cool.
I totally agree. So maybe walk us through how you solved the problem, right? In terms of, I know you had some data management constructs that you used as a basis, but give us a quick overview in terms of what your solution is, and then maybe backtrack a little bit and say, what were the data management design patterns that kind of informed where you ended up?
Yeah. So the first thing I did was look at common data management architectures that are already out there, right? I said, I don't want to reinvent anything. I really don't. I want to just use what's there. The goal is to help the customer as quickly as we could. So we first looked at the most common design or data architectures that are out there. One was data lake, bring everything to one place, run my analytics, send my results back out where they needed to go. That would not work in this case because of the sheer volume of the edge and also the intermittent connectivity.
Mm-hmm.
I would get data sometimes I wouldn't, but the edge still needed analytics done. They still needed to make decisions out at the edge, even disconnected. So we threw that one out. And the next one we looked at was, what if we move the applications out to the edge?
Mm-hmm.
And just move the applications out there and everything would be great. I could do all the analytics at the edge and that would work. And when we looked at that, we said, yeah, this looks very promising. But then the customer said, well, we also need to run analytics across the edge, meaning I'm gathering data from the edge and running analytics on the aggregate, not just on the individual data feeds coming through.
Mm-hmm.
Said, all right, so moving the applications just out to the edge doesn't quite work. And then I remember, hey, we've done some work in something called the Collaborative Cancer Cloud through an architecture called the data exchange, which says I'm pushing analytics out to the edge and pulling the aggregate in together.
Mm-hmm.
And if I pull the aggregate in together, then I can run my analytics there. I said, that's going to work. I said, that's what we need to do. And then I learned something else from the customer, that the edge was not static. It was very dynamic, meaning some nodes are coming in, some nodes are going out. And I'm like, well, I can't. The data exchange requires a static, I need a well-known edge. I know what all the edge nodes are. I've exchanged security keys. I know where all my data sources are, and they're coming in. They said, well, that's not what we have. We have assets moving in and out of the ecosystem all the time. I said, well, you guys are asking for the impossible, which they said, no, we know you can figure it out. So then I went, okay, these three don't work, but there's parts of the three that do.
Right.
So then I went and I grabbed my design patterns book from college, right? And for all you youngsters out there that don't know what the design patterns book is, you need to go buy one. It's pretty incredible because you can see what common design patterns are used for what types of situation. And I looked at a design pattern called the data stream design pattern, and I went, wow, we can make this work.
Nice.
And the data stream, it's like 30 years old. It's an old design pattern, not a new one. And I said, this might have something to it. So I started delving into design pattern, to data streams more. And it's typically implemented with something called a publish and subscribe hub. So, and I said, well, there's plenty of pub sub hubs out there. You got Apache Pulsar, you got Kafka, Redis, tons of message buses. Even ZeroMQ can do a pub sub hub. And I said, all right, let's play around with this idea a little bit. How can I create data streams in this architecture that allow for consumers and producers quickly and dynamically, because they're decoupled? It fit. It said, yeah, this is going to work. So that's kind of how we led to that first discovery on, hey, we could use data streams to make this all work.
Well, so I look at that and I think, okay, so this has well-established roots, right? That if you're an IT professional, there's a good chance this is something that you already know and are comfortable with. You're using a lot of, I mean, like you said, there's a ton of pub sub hubs. The data management structure is very well known. If I put those two things together, what I want to think is this is something that IT folks will understand. It isn't going to take a ton of training to get them up to speed on. So putting together an architecture using those types of foundations, that's it's not a massive lift to say, here's the whole new skill set and go back and train yourself for the next year, and then maybe you're ready to adopt. Can you talk through that a little bit? Like, is this as easy as it sounds, or is there more to it?
I'm glad you brought that up, because when we took this back to the customer, they go, okay, yeah, that's something we understand. We already have a pub sub hub, but what you're suggesting, Darren, doesn't work. I said, well, what do you mean it doesn't work? He says, well, because Pub Sub Hubs, I have to allocate topics ahead of time. I have to create this Pub Sub Hub ecosystem statically ahead of time. I have to know everything ahead of time. And how do I do that effectively? And I want to be able to do this quickly. I want to be able to turn new capabilities into the ecosystem quick. And I found that when I work with Kafka or when I work with Apache Pulsar, setting up those data streams is difficult. It's hard. Setting up the security, all that part. And I went, oh, crud, I got to go back to the drawing board. So I took my background in DevSecOps, which I've got a long, before it was called DevSecOps, back in the good old days where you had CVS and people don't even know what that is, RCS. And I said, all right, how can we package up data streams into something that's consumable or composable in the DevSecOps pipeline? And I said, okay, so what do I need in order to do this work? I have a data transform, an AI algorithm or deep analytics, whatever I'm doing, I'm transforming data or sets of data from one thing to information coming out on the other end. And I said, all right, what if I could bundle that together with data stream definitions, input stream and output stream definitions? So I created this bundle that I could push through the data ops pipeline. And then when it got deployed, it would automatically create data streams in the Pub Sub Hub and set up all the security for it. Wow. I said, whoa, wait. That simplifies everything, right? The developer only has to worry about the algorithm now or the AI model. And all of the complexity of setting up a Pub Sub Hub and securing it, we can take care of in a generic way. So that was kind of our approach. We said, oh, all right, so how am I going to do all of that? We looked at another 5 or 6 design patterns to come up with all the rest of the parts to simplify that complexity of working with the Pub Sub Hub.
Wow. So as always, I'm really impressed by that, because I do think one of the bad tendencies of engineers is that we love to solve hard problems with even harder solutions.
Yes, that is true.
And really, and to essentially attack a problem this hard and do it with that level of simplicity, I think is just a thing of beauty, because we all know, like, at the end of the day, to be able to deploy it and maintain it and have it be something that's used, if you can make it simple and easy to understand and easy to keep up to date, that is a way better solution than something that's the antithesis of that, right? So,
well, I don't think I would have gotten there, frankly, if I would have known the whole problem space up front.
Really? Okay.
No, I truly believe that, because as we would make some progress and then show it back to the customer, they go, well, what about this? And what about, or can I still use that? And then it made me scratch my head and go, well, wait, I understand something. So to me, I thought it was great because we were doing like co-architecture and discovery at the same time. And it was this really tight iterative process that we used with the customer, meaning, what about this? And we would, I would say it was all slideware, but it wasn't, because we were simulating some of the stuff at the same time as we were progressing the architecture. So to me, that was one of the key learnings, was to do an iterative architecture with the customer in the loop, saying, all right, this is what this will provide. And they go, well, that's good. I like that part, but you're still missing this other part. And I could go back and say, all right, we can make some architectural changes.
Nice.
That fundamentally changed the implementation now at the beginning. So I think that helped out quite a bit.
That makes total sense. So yeah, good stuff. So there's another set of questions. So obviously you're involved with what's happening at the edge, and at the edge you can have some really hard constraints with respect to how much compute, right? So if you could kind of walk through and say, like, what are the, how heavy is this, and does this really have a place if you're really limited in terms of your well, in some parlance, it would be you swap constrained, right? How does that fit in? And then what does it mean when you aren't limited and you really can load this up for compute? How can you really leverage it in those
Yeah, I'm glad you asked
two
that
very
question,
different
because that was
environments,
another,
right?
yeah, that was another discovery that
Mm-hmm.
we had. I do most of my development in the data center, and especially in the cloud, which means I have unlimited resources. All right. So my application, so what if it takes 2 gig of RAM? No big deal, right? Um, I have done that before, right? I'm just going to include Splunk Splunk is huge, right? I can't do those sorts of things. So when we started talking more with the customer, they go, well, yeah, I want this running on the edge. It needs to run out there in a size, weight, and power constraint, swaps constraint.
Mm-hmm.
And I said, okay, well, what do I get? Like 16 cores, 32 gig of RAM? He says, 2 cores, 4 gig of RAM tops on some of the edge. And they're Atom chips, right? They're not like big old Xeons or anything like that. And so I'm like, okay, so the fundamental part of managing the data streams and having the algorithms out there, that part that I automatically manage the data streams, that needs to be very, very small
Mm-hmm.
and as lightweight as I can possibly make it. So I started ripping stuff out. I started saying, well, I don't really need that. That can go. Or I had some third-party packages that just made it easy to do some things so I wouldn't have to write the code. But it came with a whole bunch of stuff with
Right.
it because they were using third-party packages. So I had to go, well, you know what? I could easily write that instead. It's simple. The algorithm that I need there is a simple, so I'll just write that part myself. And I strip things down to the bare metal, or the bare metal, to the bare minimums,
Mm-hmm.
so that I could get the stream manager part of this as small as I possibly could. And now we're under 100 megabytes for the
Wow.
stream manager and a Saber, as we call it, um, uh, running out there at the edge. And I think we can maybe even get that under 50 meg if I try even harder, which I want to do.
Of
I want to
course.
get to that point where I can say I can run this on a watch, right, on a smartwatch or something like that,
Right.
and that it can handle things. The other thing that we learned was the algorithms that are doing the inference, which I don't do any of the inference stuff at all. I don't
Right.
do any of the data analytics. I'm just providing a container for that to happen in. We want to make sure that we're giving as many resources to that data analytics as possible, and that it's flexible enough so that these Sabers, as we call them, can run anywhere on the edge, in the cloud, in a data center, on a big Xeon server with 2 terabytes of RAM, all the way down to a 2-core Atom chip with 2 gig of RAM, or whatever the case may be. That the Sabers are portable, that they can go anywhere and create this dynamic mesh based off of the type of algorithm that needs to run and the resource requirements that they have.
Okay.
So
So
that was the goal.
so what it sounds like then is really because and we haven't actually called this by name yet. So this is the sentient agent bundle resource, or the Saber architecture. And so it sounds like what you're able to do with the Sabers is your overhead for running your system is quite low, but what really sets your system requirements is how much data do you have and what kind of analytics do you need to run on it. And that's
Correct.
really what determines your system. And so you can really, as you said, run this anywhere. And then, the real question on can you run it as lightweight as you want on the edge is, hey, what is your data and what are you trying to do to that data? And what kind of,
Right.
how are you going to support that? And same thing with respect to memory and storage. So that sounds enormously scalable and really like take it anywhere, do anything with it. Just make sure you understand how you have to process your data.
Right. Exactly. For example, I run Sabers on my laptop. It's 32 gig of RAM laptop. It's not even our latest Intel processor. I think it's like a Gen 9 or something like that. and we're up to like 13. So I need to talk to my
You need to talk
management
to
and get a
IT.
better.
Yeah.
Yeah, I need to talk to IT. I can run 100 Sabers easily on my laptop that are doing minimal data transformation.
Okay.
So
And then just to
that's
make sure I caught this point. So within the actual Sabre, within this bundle, you're able to pull down whatever your analytics are, right? In terms of like whatever whatever your models are, whatever your code is, it's actually going to do your data transformation. So can you talk about like what is, does this all fall apart when you have to update a model? And are you talking about being
good.
being stuck with like a massive download in a constrained environment if so please.
You brought up another question that our customer had, right? And that is and they asked me, Darren, we've got these AI inference models out at the edge now. Great, right? Because I'm doing inference on 4K cameras or IR data or radar data, whatever the case may be. And what if I need to update the AI model? What do I do? Because I could have thousands of these spread all over of the same type of analytics that are running. So in Sabre itself, we created a learning data stream. I call it the learning channel, which is kind of funny. And what happens is all the Sabres of the same type running the same analytics are connected to each other in the same way, where I can handle intermittent comms. I can cache things. All that intermittent comms is all handled for you. And then I'm only sending deltas to the models through these data streams. So it's the same mechanism that I use to do the data analytics, but it's a back channel, for no better word, that is encrypted and protected and attested. All the things I need to secure it. But that helps the data models stay in sync. Mm-hmm. So if, let's say, you're doing object detection, Anna's doing object detection, and I'm doing object detection on the same type of data. When I get an update, Anna gets an update too, within a reasonable amount of time, depending on your connectivity. Mm-hmm. But the goal is that these models live not centrally, but throughout the whole ecosystem of Sabres.
That makes sense.
So that's
which is another
we had to add that back channel because the customer, right?
So give us a little bit more description on your data streams, right? And like what kind of data streams you need for what types of situations. I think that would be helpful.
Yeah, that's a good point. This is where DDoS came in and where I got schooled from the customer again, right? Most of the time when people think of data streams, they think, oh, I'm connected all the time. Or if I'm disconnected, I'll just cache the data. And then when I reconnect, just send the data. Well, they told me, well, can you resend the data on a 54K modem? I went,
no.
What? No, I can't send because I've got gigabytes of data I got to send. And they go, well, that's not going to work. So we came up with this concept on the data streams, and we call them data channels. And this is actually pretty cool. I was happy with this. Was like, wow, this works cool. We used a policy strategy design pattern, which says that policy can dictate when certain channels on the data stream are active and not active. And a channel is defined by policy as well. So I could have a channel that would be like a real-time channel where I'm sending all the data that I've transformed, I'm sending on the real-time channel all the time. But I can also create another channel called a historical channel, where I'm maybe aggregating the data aggregating the data in a temporal space, where I say, I'm going to give you a statistical model of the data in 15-minute intervals or a half-hour interval. And then you can have a summary channel that says, I'm going to update just the summary of what's happened over the last half hour, and that's all I'm sending. So just the summary of the last half hour.
Right. So you can get the what comes across on a data stream can be quite small, right?
It can be very small. And the cool thing about it is the consumer of that data stream, All they know is that I've subscribed to a data stream, and the channels are known throughout the whole ecosystem because the policies can be applied across the whole ecosystem. So no longer does the algorithm have to know about um, how to connect to what channel, or that all
Mm-hmm.
that stuff is handled for you in the stream manager. So the algorithm goes, "Hey, I just got information on the summary channel." That means that maybe that downstream somewhere else was running in a DDoS environment where they could not communicate for a long period of time.
Mm-hmm.
And now they've prioritized how they're going to send data. I can only send the summary because that's all the bandwidth I have right now. So they prioritize. I send summary, I send historical, and then I send real time and see how much I can pump over this network connection that I have for maybe 5 minutes.
Okay.
So it doesn't starve the upstream data analytics that are happening on that data stream. It will feed it as much as it can possibly give it in through these different channels. And the cool thing about it is the channels are defined across the whole ecosystem. So there's consistency throughout the whole ecosystem, and that's one of the beauties of that architecture.
Nice. So it sounds like then there's upfront work in saying, what is your system and what does that system need? What's the expectation with respect to communications, as well as your sensor types and your analytics? And then you need an intelligent design around your policy so that it really executes the way you need it to look. How easy is it to set your policy in place and get that into your sabers?
It's that was one of the things that we had to put up front.
Mm-hmm.
Is we had to make it easy to define the channel policies, both creation and activation and prioritization. Those are the three types of policies that we have. Very easy. It's all JSON configured in JavaScript. If you need to write um, code in there where you're doing really fancy things with the channel. So it's very straightforward and easy. And what we found was, or people that were doing distributed edge were writing these policies anyway, but they were hard coding it in the applications themselves.
Oh, wow.
So there was no consistency across deploying multiple applications on the edge. So we saw a lot of non-reuse, if that's a word, a lot of duplication of
Right.
effort. Because I would deploy one capability and I'd have to know what all the comms links were and their bandwidth and all that stuff. I'd have to know all that up front. With this and the idea of the data streams, I can deploy individual sabers that can take advantage of lower end sabers that are doing object detection and change that into tracking an object through multiple edge devices. And I can add, an object disappeared. That could be another saber. Or I can say, hey, there's two objects that look the same in two different places, another saber. So I can add new capability very quickly by taking advantage of the data, the saber network that's already established, and all those data transforms that are already out there that are working. And we've done this with the customer. They were like, "Oh, I want to do this." I said, "Oh yeah, I'll have that to you this afternoon." What? I said, "Well, I'm just taking advantage of all the underlying sabers that are already there." Oh wow, that's one of the powers of this architecture.
Because what it sounds like to me then is this is a system that is very easy to keep current with whatever new capabilities are coming out, right? So we know AI is moving at lightning speed. There's new stuff every day. Then this system is really designed in a way that, hey, if you've got a new model and you know where you want to use it, you make a new saber for it and you get it into you get it in with the right policy, and now, or actually maybe not even a policy change, right? You just say, here's the existing policy that you can use to control this new saber, and now you can spread that across,
Everywhere,
across your entire mesh, right? So
yeah, in fact, one thing we're working on in the DevOps pipeline is in the deployment model. Where do I deploy my sabers? We're working really hard right now so that the devices can advertise their capabilities. and what they're connected to,
Oh,
meaning
beautiful.
what sensors they're connected to.
Mm-hmm.
So when I drop a saber in, I can describe in a saber what data sources it's looking for, specific like sensors, and also what the capabilities are that it requires. Do I need a GPU? Do I need an FPGA or a neuromorphic processor or things like that? And then the sabers would automatically deploy out. We want to get to that point because that would be
I
super
was going to say
cool,
that
right?
sounds way too easy, right? Like where are the days and days of work to like do that
Oh, I got to
manually,
target.
right?
Yeah, right. So we really want to get to that point where the sabers can be very dynamic. Even if I have a node go down, right, or I'm overwhelming, maybe it's a gateway that is doing sensor fusion, right? Maybe I'm overwhelming that. Maybe I can move a saber to a box sitting next to it and still get all the data feeds coming in and do all the transformations on a bigger box because maybe the AI algorithm's more intense. So I need more cores. I need a GPU or NPU to do it effectively.
Which
That's where we want to do that more dynamic. The Saber network itself, hey, I don't care. They're completely decoupled. They can connect to each other through the pub sub hub. So
based on what you're describing, there's a real way to use legacy compute in this, right?
absolutely.
Obviously, there's some things that have to be done with respect to the data, and more specifically the algorithms to say can they be run on the existing compute. But to me, it sounds like this system is also flexible enough that if there's a real compute limitation at the edge that is can't really be changed out or augmented, that you could really focus in on that, use the super lightweight sabers, and then say, can we get that algorithm down small enough that there's really a path to using it? Well, or maybe the better way to say it is, how would you do that, right? If you're really constrained
Well,
like that.
yeah. You could even put a saber that's a pass through.
So explain that.
Well, all it does is collect the data. Maybe I do have a very small footprint and maybe it's old. I can run a saber on there because they're pretty lightweight. I can run a saber on there that is just connecting it to the pub sub hub, and it's just a pass through. It's not doing anything except grabbing the data and publishing it into the saber network.
So you then can take advantage of where you do
I
have
can
compute,
take advantage.
right?
Yeah,
And
exactly.
obviously there's still a network constraint piece of that, but that means there is a clear way to work around that isn't re-engineering, that isn't adding in a new box or anything.
Right. And yeah, the other option is to add even a small NUC, right? Even an Intel NUC, I can add it sitting side by side, very lightweight and small. I can add it right next to a box that maybe doesn't have a network connection or any way of talking outside, except maybe a USB or an RS-232 cable.
Wow. Perfect.
All right. Connect that into a NUC, and now it's in the Saber network. So now I have a new data feed. I can do tons of stuff with that data now.
Beautiful. And I know we need to get close to wrapping up here, but I do, and I'm going to ask you the hardest question with no time left.
Oh no.
Right? Which is, we all know that none of this can be put in place without a way to secure it, so that the data that's being transferred is well controlled and well monitored and protected. So can you just do a high level of how you've approached security with this with your Saber architecture?
Yeah. So yeah, that's a great question. First, easiest thing, right? That they're going to say, well, of course he's encrypting the data streams. Absolutely.
Right.
I have to encrypt the data streams. The keys are generated for data stream encryption and decryption in a rotating manner. And that happens at build time, where I establish a root of trust and attestation of the sabers. So when they get deployed, they can be targeted to specific categories of machines that I trust. The reason we had to do that is a saber, if it got out in the wild and could just be deployed anywhere, someone could take a USB key with the saber, plug it into anything, and now I could connect to the saber network.
Yeah.
which
Not
means I
good.
could feed it with garbage. I
Right.
could feed it with tons of erroneous data. So we set it up so the sabers themselves are encrypted, and they can only be decrypted on boxes that I have attested to.
Beautiful.
Which is critical. That prevents spoofing and snooping of data on the data streams. So those are the mechanisms that we used to secure the sabers.
Beautiful. Perfect. Well, I think we are close to wrapping up, but and I said that was the last question. Of course, it wasn't. Is there anything else that we haven't covered that we ought to be talking about with the sabers and how that architecture works?
It has been a journey to do it, and I appreciated the process probably even more than the end result, which was we did a really cool way of doing iterative architecture with the customer, because we could simulate the architecture and find holes in it and get feedback from the customer as we went through this, discover what they knew inside them, but they didn't know that they knew by showing them things without writing a ton of code, right? To make it all work for them in the simulation. So to me, that was probably one of the most critical aspects of doing this work. The sabers themselves, I think they're pretty cool little technology, but I couldn't do it without the partners that we worked with. Our idea was, let's use what's already out there if we can. So we're using Apache Pulsar, and we're using vendors to bundle this all into a nice package and sell it with our partners. So I think that's the direction that we're headed.
That's great. And then my understanding is you're not married to Apache Pulsar, so if somebody needs a different pub sub, you've got with very little code changes, you can easily work with whatever software the customer prefers, right? You got some good flexibility.
Well, and that was another thing that we found too. We needed to put an adapter pattern in place so that we could plug in a different pub sub hub, a different security key generator, or authorization mechanism. So, or even deployment mechanism. So we have abstractions for that. And frankly, I don't want to do that work. I'm kind of lazy. I want someone else to do that work. So I'll just put an abstraction layer in there and call their stuff. That's the key.
Perfect. Well, Darren, thank you so much. We really appreciate your insight on this. I know you've got additional collateral too that you're going to attach to this webcast. So just know, if you're curious, there's a lot more information to be had and a lot more detail that is in more of a written form. And Darren, impressive stuff.
Thanks, Anna.
I see a lot of solutions out there that are extremely elegant and super hard to actually use and take advantage of. So having something that folks can understand that takes advantage of their current knowledge, and it's a thing of beauty. So thank you for the thank you for the detailed dive on this, and appreciate your time today.
And thanks for hosting. I appreciated it. It was wonderful to be in the interview seat.
Well, a nice change if nothing else, right?
Thank you for listening to Embracing Digital Transformation today. If you enjoyed our podcast, give it 5 stars on your favorite podcasting site or YouTube channel. You can find out more information about Embracing Digital Transformation at embracingdigital.org. Until next time, go out and do something wonderful.